NASA's Curiosity rover just drilled into a rock structure that looks like a spider web. It's called boxwork, and it shouldn't be here. When the rover analyzed the powder inside, it didn't find just rock. It found a chemical signal that on Earth is only created by one thing: life. These aren't just random atoms. These are fatty acids, the skins of living cells. And finding them preserved in a 3 billion-year-old crater changes everything we know about Mars. So what exactly did NASA's Curiosity find inside the mudstone? Curiosity landed on Mars in August 2012. It touched down inside Gale Crater, a wide, ancient basin roughly the size of Connecticut, and it has been there ever since. Rising from the center of that crater is a mountain scientists call Mount Sharp. It's roughly 3 miles tall. And embedded within its slopes are layers of rock that each tell a different chapter of Martian history, from an era when the planet had rivers to the long, dry age that followed. Since 2014, Curiosity has been slowly climbing those foothills, sampling rock as it goes. It carries a miniature chemistry laboratory inside its body. That lab is called SAM, the Sample Analysis at Mars Instrument Suite. When the rover drills into a rock and delivers the powder to SAM, the instrument heats the sample and measures the gases that are released. It is, in essence, reading the chemical signature of Mars from the inside out. What the science team was looking for is organic molecules. Organic molecules are carbon-based compounds. They are the building blocks of life, as we know it. They can be formed by living organisms, but they can also arise from geological processes with no biology involved at all. Finding them doesn't confirm life, but not finding them would have been devastating. And so, when Curiosity began detecting them, the team paid very close attention. The most significant of those detections came from a rock sample nicknamed Cumberland. Curiosity drilled into Cumberland back in May 2013, during the rover's 279th Martian day of operation. The sample came from a location called Yellowknife Bay, a flat, ancient expanse of fine-grained mudstone that the team had diverted to study before heading toward Mount Sharp. One look at the geology told them it had once been underwater. The sediment it pointed to a lake that had existed for millions of years. The Cumberland sample was remarkable. It was rich in clay minerals, which form in the presence of water. It contained sulfur, which can act as a preservative for organic material. It had nitrates compounds that on Earth are essential to plant and animal life. And it carried a type of carbon-based methane that, on Earth, is associated with biological processes. Scientists analyzed that sample multiple times using different techniques over the course of more than a decade. Each experiment revealed something new. Then, in March 2025, researchers announced what may be the most significant finding yet. Locked inside the Cumberland mudstone were 3 molecules: decane, undecane, and dodecane. These are hydrocarbons. They are made of long chains of carbon and hydrogen atoms, and they are the largest organic molecules ever detected on the surface of Mars. Now, to understand why this matters, you have to understand what these molecules are and where they typically come from. Decane has 10 carbon atoms. Undecane has 11. Dodecane has 12. They belong to a class of molecules that are closely related to fatty acids. And here's the thing about fatty acids. On Earth, they are not incidental. They are fundamental. They are the main component of cell membranes, the walls that define the boundary between a living cell and the world around it. Almost every living organism on Earth produces them. They are, in a very real sense, one of the signatures of life. They can also, in certain conditions, be formed without life. Hydrothermal activity, certain chemical reactions deep in rock, these processes can generate fatty acids too, but they tend to produce shorter chains, and they do so in smaller quantities. The molecules Curiosity found were long chain. That detail matters. Scientists believe the rover did not detect the fatty acids themselves directly. What SAM actually measured were the breakdown products. When the sample was heated to extreme temperatures inside the instrument, the fatty acids, if that's what they were, would have shed their oxygen atoms through a process called decarboxylation, leaving behind the alkane chains that SAM then identified. To verify this, researchers in a laboratory mixed undecanoic acid, an 11-carbon fatty acid, into a Mars-like clay. They ran a SAM-like heating experiment, and exactly as predicted, the acid broke down and released decane. The chemistry matched, the prediction held, so the data strongly suggests that what Curiosity found inside Cumberland were the preserved remnants of fatty acids, not the molecules themselves, but their shadows, still readable billions of years after being laid down in ancient sediment. But here's where it gets strange. When scientists tried to account for those molecules using known non-biological sources, they ran into a problem. The quantities didn't add up. Meteorites strike Mars. They have done so throughout the planet's history. Those impacts deliver organic material, carbon-based compounds that arrive from across the solar system. That's a known, non-biological source. There is also a hypothesis that Mars once had an organic haze in its early atmosphere, similar to what is observed today on Saturn's moon Titan. Organic particles from that haze could have settled onto the surface and been preserved. And yet, when researchers published their findings in the journal Astrobiology in February 2026, they concluded that these sources' meteorite delivery, atmospheric haze, known geological reactions could not fully account for what they measured. To understand why, they had to work backward in time. Mars has no global magnetic field. It has a very thin atmosphere. This means the surface is constantly exposed to ionizing radiation from space high-energy particles that, over millions of years, break apart complex molecules. The Cumberland rock has been exposed at the Martian surface for roughly 80 million years. That is a long time to be bombarded by radiation. So the team used laboratory radiation experiments, mathematical modeling, and Curiosity's own data to rewind the clock. They estimated how much organic material would have been present in that rock before radiation began destroying it. The results were striking. Before exposure, the mudstone likely contained somewhere between 120 and 7,700 parts per million of long-chain alkanes and fatty acids. That is a wide range. But even the lower bound represents an abundance that no non-biological processes struggle to explain. The researchers stated their conclusion carefully, as the non-biological sources they considered could not fully explain the abundance of organic compounds. It is therefore reasonable to hypothesize that living things could have formed them. That is not a confirmation of life, but it is not nothing. It helps to put this in context. Curiosity is not the only rover on Mars looking for signs of life. Its younger sibling, the Perseverance rover, has been exploring Gale Crater since February 2021. In September 2024, NASA announced that a sample collected from a rock called Chayava Falls showed what researchers described as a potential biosignature spots of iron-rich minerals arranged in patterns that, on Earth, are associated with microbial activity. NASA's associate administrator called it the closest we've actually come to discovering ancient life on Mars. Officials were careful to note that non-biological explanations could not yet be ruled out. The combined picture from both rovers is beginning to suggest something consistent. Mars is not chemically inert. Its ancient rocks carry organic material. That material is more complex and more abundant than simple non-biological processes can easily explain. The Curiosity finding adds another layer to that story. Cumberland's mudstone shows a distribution of organic compounds, aromatic molecules, sulfur-bearing compounds, aliphatic chains that, as researchers noted, bears a stronger resemblance to what you find in biological kerogen on Earth than to the organic compounds detected in carbon-rich meteorites. That pattern does not prove life, but it is the kind of pattern you would expect to find if life had once been present. Scientists describe it this way. They are not saying biology is the answer. They are saying biology is a reasonable hypothesis. Meanwhile, curiosity itself has not stopped moving. In May 2025, the rover arrived at a region of Mount Sharp that no spacecraft had ever studied up close, a terrain scientists call the boxwork unit. When viewed from orbit, this area is covered in low, crisscrossing ridges, arranged in a pattern that looks, from high above, almost like a spiderweb. These ridges are believed to have formed billions of years ago, when groundwater trickled through cracks in the rock and deposited minerals that hardened like cement. Over eons, Martian wind eroded the softer surrounding rock away, leaving the harder mineral veins standing as ridges. The science team divided their exploration of this region into 4 phases. For the first half of 2025, they approached, observed, and began to understand the structure of what they were looking at. By June, they drilled their first sample, a rock called Altadena, to begin the chemical analysis. By November, they had drilled into a ridge target they named Nevado Sajama, after the highest peak in Bolivia. Then, in early February 2026, the team did something they had only done once before in the rover's entire 13-year mission. They used the last of 2 small containers of a special chemical reagent called tetramethylammonium hydroxide, or TMAH, to treat a drilled rock sample before analysis. This solvent makes certain organic molecules detectable that standard heating would otherwise miss. The team had been waiting years for the right moment to use it. When they found clay minerals in the boxwork region clay that can protect organic material, they decided the time had come. The last time Curiosity used TMAH, 6 years earlier, the results revealed organic molecules that simple heating had not detected. The team spent 7 months interpreting those findings. For this final experiment, they redesigned the method, running it in 3 stages to more closely replicate laboratory conditions on Earth. They rehearsed the steps. They ran a test handoff of the sample before committing to the real experiment. As of February 2026, Curiosity has begun that experiment. The data is still being analyzed. Here is what we know so far. Mars once had liquid water. It had it for millions of years, possibly much longer. It had chemistry that could concentrate organic molecules in fine-grained sediment. It had conditions, at least in some places and at some times, that scientists describe as habitable. Inside the ancient mudstone of Gale Crater, something preserved complex organic molecules across billions of years, through radiation, through oxidation, through the slow death of an entire atmosphere. And the quantities in which those molecules were preserved exceed what known non-biological sources can account for. That is the honest summary of what the data shows. Not a discovery of life, not a confirmation. Something more difficult and more interesting than that, a gap in our explanations that keeps getting harder to close. The researchers themselves quote Carl Sagan. Extraordinary claims require extraordinary evidence. They know what they have is not yet extraordinary enough to make the claim. They say so directly, but they also say something else. The chemical story preserved in Martian rocks may be more complex and more intriguing than previously thought. And Curiosity is still climbing. It is still drilling, still delivering samples to SAM, still sending data back across hundreds of millions of miles of empty space to a team of scientists who sit at computers in Southern California and read the chemical fingerprints of a planet that may, once upon a time, have been alive. We haven't answered the question yet, but we've never been closer to asking it in the right way.